Isn't that bizarre? All right, I think we're good now. Thanks for letting me know. So in this, we measured the difference, the total pressure, and then the static, because through Bernoulli's equation, that's related to 1/2 v squared, and so we can calculate airspeed g. And that's because at p0, the velocity is 0, the flow has gone to 0, and so that difference is directly given to the velocity. So let's do an example. Let's say a pedostatic tube measures that difference to be 10 inches of water. So immediately you go, that's not standard units for pressure, right? So what we're saying is that we have a manometer connected up to these tubes, and the manometer measures a height difference of 10 inches. And so we have to use the manometer equation, because it's a manometer measuring the pressure difference, to get the pressure difference. So the manometer equation rho GH. Oh, we were told that at 10,000 feet, airplanes flying in this pedostatic tube. So you're looking at the formula. We say we're at 10,000 feet. So the density of 10,000 feet, assuming standard atmosphere, is that. And we're going to use sea level as well, so let's write it out. Zero zero 17556. Better. So we're at 10,000 feet. Here's our density at sea level. Standard atmosphere, we get this. We have a pedostatic tube measuring that. So we use the manometer equation. And if you're not paying attention, you might be tempted to plug in 10,000 feet here, because it's h, right? But h is in the equation is not the altitude of the airplane. It's this distance on the manometer, because it's the manometer equation. So we have to make sure we plug in 10 inches here. That's gravity. If we get completely confused, we might be tempted to plug in this density. That's the density of the air. But we know that the manometer equation needs the density of the fluid. So we really ought to write this, just to be clear. So again, these are the kind of mistakes you can make if you're just looking at the equation, you pull it out of the book and you start plugging in for variables. You have to know what the variables mean in that particular equation. All right, so the density of water we've used before. .94 slugs per foot to the third. Plug in gravity. And then we plug in 10 inches. But then we notice, oh, inches and feet, that's not going to work. So we got to convert inches to feet. We've got 12 inches per foot. So the inches cancel out. And this foot flips up to the top, cancels out foot to the third, the foot to the second, and then slug feet per second squared turns into a pound force, right? So we're going to get the correct pressure units, pound force per foot squared. So all that work was just to figure out what the pressure difference was measured by the manometer. It'd be nice if they just gave us the pressure difference in pounds force per foot to the third. But when you get into experimental methods, you'll be running wind tunnels. You'll use manometers to measure pressures, and so you'll have to use that equation. All right, so now we go back to this, and we can calculate the airspeed of our airplane flying at 10,000 feet with a pitot-static tube that gave us that measurement. So let's go back to this equation. And if you remember, there's two ways we can calculate the airspeed. One is using the actual density at altitude, and that's what we call true airspeed. And then the other way is assuming that our instrument on board the airplane, that's at 10,000 feet, this is at sea level, is assuming the instrument on the airplane can't measure density, and so we just use sea level. So with this one, we get equivalent airspeed. This one, we get true airspeed. Now, if you're working problems like this, you can go into the book and pull up the formulas for true airspeed and equivalent. I'd like you to remember that they come from Bernoulli's equation for low speed flow and the definition of total pressure. And that's what's being measured. So true airspeed uses the density of 10,000. So there's the pressure we calculated. There's the density at the altitude. And so we get 243.52 feet per second. And then if we do V equivalent, the only difference is the density that's used in here. And because the density is higher at sea level, we're going to get a lower airspeed. So this is the true airspeed. This is the equivalent airspeed if we sense that pressure difference at sea level. Well, it turns out that on a lot of airplanes that have airspeed measured with a pitot-static tube, this is what you see. You get the equivalent airspeed because there's no way for it to know the density of the air outside. And so then as a pilot, you have to remember that this is reading low to what your actual airspeed is, or you have a chart that converts for you. And it goes back to the fact that, I mean, I'm talking about like a Cessna 172 that uses pitot-static tubes for airspeed. And if you have a computer on board that takes all that information, it will correct for altitude and give you true airspeed or indicated airspeed. Like I said last time, on a car, you can get your speed mechanically from the tires. Of course, you know, if you replace your tires with much larger tires, then the RPM is less per mile driven, and so you'll actually read low on your velocity in your car. Well, the equivalent airspeed is the calculated, indicated is what the dial actually shows. So if there's, yeah, the indicated is what you're actually seeing on the dial. The equivalent is if everything's working properly and your pitot-static tube is correct. Yeah. And then there's calibrated airspeed, because sometimes typically what they'll do is they'll calibrate the airspeed on the airplane to account for the pitot-static tube and where it's located on the airplane, and how the flow goes into that tube actually when it's installed on the airplane. Yeah. Um, yeah, so I'm not a pilot, but you might correct me on this. That is so that you can adjust your altimeter to give you that altitude. You set your adjustment, you set your altimeter in your airplane to match what your known altitude is on the ground. I'm not sure what they give you as far as the density altitude. And so they're giving you your equivalent altitude based on the air density compared to standard atmosphere. Yeah. Yeah. So that have to be a pretty hot day for it to be 3,000 altitude, right? Here, because, yeah, we're at 1,300. Okay, so the next thing we want to talk about is supersonic flow in wind tunnels. And what people found out is that when you take flow and you accelerate it by running it through a decreasing area, the velocity is going up. And if you narrow this area down enough, you can get Mach 1 in the throat. And then once the flow goes past Mach 1, the velocity will actually be going up in the supersonic region, even though the area is increasing, which seems counterintuitive, right? You think of the area getting smaller, the velocity is going to go up because more mass has to go through. Well, what happens when you get supersonic, the density changes so much that the air is actually expanding out through that nozzle. And this is how you have to get supersonic flows. You have to compress air, run it through a really small orifice, and then expand it out. That's how rocket nozzles work. You have combustion back here that creates high pressure. You run it through a nozzle, and then you expand it out, and you get high-speed supersonic flow coming out the back that gives you all of the thrust. So there's some math we can do that shows that this actually happens. And it starts with the conservation of mass. So rho VA is constant. This is for compressible flow, so this is good for subsonic, supersonic flow. And there's two ways we can derive this. One is we can take the derivative of this thing for each of the variables. And so if you do that, you get, it's just the product rule for each of these. So you have the derivative of the first part times the second, derivative of the middle, and the derivative of the second. So the product rule on the first part, second part, and that derivative is going to be 0 because the derivative of the constant is 0. The other way you can think about getting to this, and it's more algebra, is you have a point in the flow where you have density, velocity, and area, and then you move a little distance forward, and the density changes by d rho, the velocity changes by dv, and the area changes by dA. And then you write the conservation of mass between those 2 points. Which is totally valid. That's how we use conservation of mass. We say it's constant, so it has to be equal between 2 points in the flow. And if you start multiplying all this stuff out, there's a lot of it. You get a rho VA term from these three, and then you get stuff like rho VDA, and you get rho DVA. So I'm just doing all the products, and then you get d rho VA, and you're going to get a bunch of other stuff that's like rho DVDA plus d rho VDA. These are the other products, the cross product terms, and then you get what's left out here. D rho dv times a, and then when you get the d dv d rho stuff, a lot of terms here, right? And what you do here is you say, here's two small numbers multiplied together. Here's two small numbers. Here's three small numbers multiplied together. And so when you take the limit, if you take the limit and squeeze those 2 points together, all of these are small, and so you can neglect all of the double products, because you get 0.1, like 0.1 times 0.1 times 0.1, you get 0.000 or 001. And so you can neglect those in the limit, and you get the formula that I wrote up there, which is a derivative is small changes, right? So you get these same terms are equal to 0. So there's two ways you can get this formula. Either differentiate or essentially do what a derivative is you can make a small change, and then you take the limit as those changes get really small. Anyway, we're going to take this equation and do a bunch of algebra on it so that we can learn about flow when the area is changing related to velocity and density changes. So we're going to divide by rho VA all the way across the equation. We can do that because remember. So if we do that, then you can cancel out a bunch of stuff. And we get d rho dv. Still 0, because dividing 0 by a number still gives you 0. So this tells us how a pressure change, a velocity change, and an area change are all related. So we still have more algebra to do. We use conservation of mass, and now we have conservation of momentum that we can throw in here. And we're going to use the Euler equation, which isn't specialized for anything. It's just the original one that said pressure changes are related to velocity changes like that. So we derived that a long time ago, and this is the one that we integrated for incompressible flow when we said density was constant, and it's also the equation we used when we did the isentropic flow. So with this one, the magic algebra here, and it took people a while to figure this out, is let's eliminate rho here. So rho put that on the bottom. We'll stick that in here, and we get and we're just going to keep plugging along with this algebra because somebody figured this out. So hang on. And then we're going to remember that speed of sound is dp by d rho. Remember when we derived that? And then we related that to gamma RT so we can calculate the speed of sound. So that means dp by d rho inverted here is a squared, so we get an a squared on the bottom. Magically. No, it's we derived this formula like a week ago. Yeah, remember we looked at an acoustic wave moving through the air, and we tracked the flow as it went past a point, and we applied all of the equations in motion, like v plus d, dv rho plus d rho. Did a bunch of algebra, and we found out that the speed of sound is given by that. And then we substituted into this to find out that it's equal to gamma RT from the ideal gas. Yeah, we're using, to do this, we're using all of the equations we've had so far. And then if you look at this, we got a dv over v. So let's put a v down here and a v up here so they cancel out. So that we get a dv over v. Like I said, hang on, because there's a lot to do here. So now we got a v squared on the top. And then we got a plus 1 times dv over v. I'm sure I haven't dropped a minus sign here. So we're good. And the reason that people, when they finally got to this point, go, okay, this is good, because this is Mach number squared. So the algebra gave us a v squared and an a in there from getting rid of the dp's and d rhos. So if we shove this over to the other side, So from the conservation of mass, going from one point in a flow and just moving a very small distance down a streamline, we've learned that the change in area is related to change in velocity in this way. Because we got rid of the changes in pressure and density by substituting various things. Actually, changes in density, really. And yeah, changes in pressure as well. So this is the key equation that tells us for any kind of flow, if you have small area changes, what happens to the velocity. Again, a lot of algebra. Don't think that people that did this the very first time figured this out. People sat around before there was TV and internet and cell phones and smartphones and radios looking at these equations in front of the fire while they were trying to stay warm. And honestly, the reason that a lot of the scientists got to do this stuff is that they got sponsored by somebody who had money or land and had the castle with the fire that they could sit by and do this stuff. So I guess that's what you guys are training to do, is right? You get a degree, you get a job, you get money, you can buy a house with a fireplace so you can sit by the fire. And well, yeah, maybe you're messing on your smartphone, but yeah, hopefully you're doing some equations too, right? Not after work? Probably not. All right, so got to this point and they said, well, what happens if the Mach number is subsonic? So we're going to say, do some what if stuff. So the first one is, all right, we know how subsonic flow works, especially incompressible. Density is constant. We have Bernoulli's equation. We have conservation of mass where you can cancel out the densities. And for really low speed flow, we know that rho VA is constant, which is what we started off to get that. And the density can cancel out, right? And so here we get a real direct relationship between area and velocity. And we know if we increase the area, the velocity goes down and vice versa. So let's see what this equation tells us. So if the Mach number is less than 1, then m squared minus 1 is going to be a negative number. I guess I should write is a negative number, because m is less than 1, so you square it, you get a number less than 1, you subtract 1 off, you get a negative number. So what does that say about the relationship between dA and dV? Remember, so these are changes, right? So if area is getting bigger, that means it's a positive number. If the area is getting smaller, it's a negative number. So if dA is positive and the area is getting bigger, what does that mean dV is? Is dV positive or negative? Positive on the left, negative sign, dV's got to be negative. So this whole thing here, if we solve for dV, it's going to be a negative number, which means the velocity is going down. And that fits. That's low speed flow. Fits with the VA equals constant. That's our intuition that that's what should happen, right? Scenario number 2. Mach number is greater than 1. I think you can see what's going to happen, right? So now m squared minus 1 is a positive number. So same scenario, let's say A is increasing, so dA is a positive number. Positive number, so that means that dV is a positive number, according to the equation, which means the velocity is going up. So in supersonic flow, increasing the area makes the velocity goes up. And you go, why? What the heck? In this flow, especially low speed, density is constant. Here, density is not constant. And in supersonic flow, the density is decreasing so fast that the air is expanding. And so the expansion in that nozzle allows the density to expand and shoot the flow out faster. That's what's going on. So it's counterintuitive that because of this density change, when we're looking at those converging, diverging things, mentally we're saying, okay, the density is not changing, right? You see that amount of fluid having to squeeze through that area, so it's got to go faster. But here, when it squeezes, it actually squeezes the density down as well when it's supersonic. So vice versa, if you take a supersonic flow and you narrow the area down, it actually slows down. The shock wave is a huge pressure jump. We'll talk about that in like a week. But it's a pressure, temperature, and density jump. So yeah, they are related. In a shock wave, you go from supersonic flow and you go through the shock wave, and the air compresses together. You get high pressure, high density, and the temperature goes up. And it slows down to subsonic flow. So really, the energy in that supersonic flow, it's turned into density, pressure, and temperature changes increases. Yeah, zero is kind of trivial, right? If zero, then it's just there's areas not changing. Yeah, that's a good question. What does it mean? Because that's the borderline case between these two, right? And interesting things usually happen on the border. So that's case number 3. So exactly Mach 1, we get so it says that for Mach 1 flow, the area cannot be changing at that point. So what that means is, if you're driving flow through a nozzle like this, right here in the middle is where dA is 0. Because here, dA is going down, and over here, A is going down, and here, A is going down, A is going up, so dA is negative. Here, dA is positive, so it has to go through 0 at that middle point. And that's the throat, and it's only right here where you can get Mach 1. Seems weird, but in order to get flow to go from subsonic to supersonic, it has to go through that nozzle where the Mach number is exactly 1, and then over here, if you drive it with enough pressure, you get supersonic flow here. And the reason you have to drive it with enough pressure and you have to narrow the area down enough is because the flow is increasing, increasing, increasing. So you have to hit Mach 1 at that nozzle. You have to have enough pressure to drive the flow, to put enough energy in it to get Mach 1 at the nozzle. If you don't have a high enough pressure drop, the flow will increase. You won't hit Mach 1. You'll still be subsonic, and then the flow will expand out, and it will go back down to 0 on the other side. Kind of weird, but talking about. So if you go like this, yeah, because it's expanding, and then at this point, then here the velocity is going back down. Yeah, the pressure and density can go up. And then it would depend upon how much it goes down as to what happens there. If it goes down enough, it's going to hit Mach 1. And then if you have this area too small here, it still hits Mach 1 there. It's just you restrict the amount of flow that can go through. That's what's called choking the flow off, because you make that so small that you can only allow a certain amount of mass through there. Yeah, well, and this is all steady state flow. So the way that you get flow to go supersonic is the picture I was drawing at the beginning. Somehow you have to get a really high pressure, and then you run the flow through a really small nozzle so that you can get up to Mach 1 at the nozzle. So you either have a tank here. This is what our supersonic wind tunnel does. The tank has velocity of 0, so this is stagnation, temperature, pressure, and density. That means that's total pressure. It's just where the velocity is 0. And then you run it through a very narrow orifice. And this has to be small enough so you get Mach 1 here. So it has to speed up from 0 by going through here. You hit Mach 1, and you get supersonic flow here. So you can either pump up a tank or you can have combustion, like in a rocket, where you burn fuel, and all that energy goes into creating the pressure, temperature, and high densities. How are we doing on time? 1:11. If you have this picture, if you talk about a tank with stagnation velocities or values here, and then the flow goes up, you can plot, you can come up with equations for pressure, temperature, and density anywhere within the flow, like we've been talking about it. It goes from 0 velocity and high pressure. The pressure is going down as it goes through here. And so you can develop, using the isentropic equations and a bunch of other equations that's not worth our time to go through, you can develop and plot how the pressure increases and decreases through these regions. I want to pull one of the equations. This is, your textbook spends a lot of time on this, but you'll get into this when you take Aero 1 and 2. So we're going to go on to airfoils and wings. But one of the formulas gives you how the density varies with Mach number as you move through this kind of a nozzle. So really what we can tell is how much does the density change relative to the stagnation density, the density in the tank. So as it comes out of the tank, the density is going down as it goes through here. How much density change do we get relative to Mach number? So as we're going through the nozzle, here obviously Mach number is 0. As you go through here, maybe you hit 0.3. You get further in here, you get 0.5. And then you get Mach 1 at the throat. And then you get Mach 2 as it goes out. So that tells us, as we're moving through this nozzle, how much the density changes. And this allows us to examine our assumption for incompressible flow. If you remember when I defined incompressible flow, I gave you rules of thumb. And I said, well, when the Mach number is less than about 0.3, we can assume incompressible. And I also gave you some velocity limits. I said when the velocity is less than or equal to about 100 meters per second, or 225 miles per hour. Remember those? I said if you're less than this, you can pretty much assume incompressible. This equation is going to tell us by putting in different Mach numbers whether this assumption is reasonable, because we can look and see how much does the density change and decide is that small density changes, so we can say, well, we can throw them away or not. So let's make a table. I did this on a spreadsheet. I put Mach number into that formula, and then I calculated from this formula at that Mach number what the density change is. So at Mach 0, the density doesn't change at all. Makes sense because there's no flow change. Let's crank it up, go down the tube to Mach 0.1. And the density hasn't changed at that point, but about 1%. So we could live with that. We could say, okay, our calculations are going to be off by 1%, but that's good enough. Let's make the incompressible assumption and use the easy equation. Makes sense, right? Let's go up to Mach 0.2. Now we're off by about 2%. That's still not bad. Assuming the density only changes by 2% on our flow, because it's low speed, we're good. So now the ratio is 0.9564, so we're talking close to 4 to 5%. And depending on how accurate we want to be, that's starting to get to the point where we probably ought to include density changes in our calculation. Let's go to 0.4. Now we're at about 8% change. So the cutoff is not hard and fast. It's really more of how much error can you live with, or how much is tolerable. So we could even go up to like Mach 0.4 and say, well, we're only going to be off by 8%, but that's getting to be pretty big as far as engineering calculations go. And so that's where this rule of thumb came from, is that if you're less than Mach 0.3, which is about 100 meters per second, or 20 to 25 miles per hour at sea level, then you can say incompressible flow is a pretty good approximation. Oh, yeah. And if you want to be 100% accurate, you should use the compressible flow equations all the time. But they're a pain. So if you want to get within 1% accuracy for low speed flow, you can use Bernoulli's equation and the conservation of mass equation. Or if you're doing water, now remember this is for air, because we put in gamma for air. If we're talking water, water doesn't compress unless you have really high pressure, so it's incompressible all the time. Almost, approximately. All right, let's wrap today up. We've covered most of the flow regime, all the way from low speed flow up to supersonic flow now. The next thing we want to talk about is viscous flow. And this is flow near a surface. And what happens is the molecules of air hit the roughness in the surface and they slow down because of that friction. So we need to be able to predict that as well, because that's where a lot of the drag of an airplane comes from. So we'll start on that next time. And I assigned another homework. I printed it out, but I forgot to bring it. Am I remembering right? It's due next Wednesday. The quiz is on Friday, and so we'll go over it on Wednesday. I think we're right. I think I'm remembering that right. I'll look. All right. Have a good weekend. Enjoy the hot weather.